Welcome to the fascinating world of Faraday's laws of electrolysis. Discovered by Michael Faraday in 1834, these laws laid the foundation for modern electrochemistry, enabling industries from metal refining to green hydrogen production. In this presentation, we will cover the first and second laws in depth, work through 5 interactive quizzes and 5 detailed problems, and then revisit all core concepts in a comprehensive summary. Faraday's first law states that the mass of a substance deposited or liberated at an electrode during electrolysis is directly proportional to the quantity of electricity passed through the electrolyte. Mathematically, M is proportional to Q, or M equals Z times Q, where Z is the electrochemical equivalent of the substance. The constant Z is the mass deposited per unit charge. For a constant current, Q equals I times T. The same substance always has the same Z value, giving a linear relationship between mass and charge. Faraday's second law states that when the same quantity of electricity passes through different electrolytes, the masses of substances liberated are proportional to their equivalent weights. The equivalent weight E is the molar mass divided by the valence of the ion, so M is proportional to M over V. This means the electrochemical equivalent Z equals 1 over F times M over V, linking both laws into a single unified expression. F is the Faraday constant, 96,485 coulombs per mole. The two laws combine into a single powerful equation. M equals I times T times M divided by F times V. The Faraday constant F equals 96,485 coulombs per mole and represents the charge of 1 mole of electrons. It equals Avogadro's number multiplied by the elementary charge. This equation allows us to calculate the mass of substance produced in any electrolytic process with constant current. The number of moles N equals I times T divided by F times V. Water electrolysis is the quintessential example of Faraday's laws in action. When an electric current passes through acidified water, water molecules split into hydrogen and oxygen gases. At the cathode, water is reduced to produce hydrogen gas and hydroxide ions. At the anode, water is oxidized to produce oxygen gas and protons. The overall reaction shows that 2 water molecules yield 2 hydrogen molecules and 1 oxygen molecule, producing a 2-to-1 volume ratio of hydrogen to oxygen. Faraday's laws underpin a vast range of industrial processes. Electroplating deposits thin metal layers like chrome on car bumpers, gold on jewelry, and silver on cutlery. Copper electrorefining produces 99.99% pure copper while recovering precious metals as anode sludge. The chloralkali process is one of the largest volume chemical processes. The Hall-Héroult process extracts aluminum from bauxite. Water electrolysis is emerging as a key technology for green hydrogen production. Understanding the difference between electrolytic and galvanic cells is crucial. In a galvanic cell, a spontaneous redox reaction generates electricity with negative delta G. In an electrolytic cell, electricity from an external source drives a non-spontaneous reaction with positive delta G. In a galvanic cell, the cathode is positive and the anode negative. In an electrolytic cell, the cathode is negative and the anode positive. However, electrons always flow from anode to cathode in both cases. Michael Faraday was one of the greatest experimental scientists in history. Born to a poor blacksmith family in 1791, he became a bookbinder's apprentice and taught himself science from the books he bound. He discovered electromagnetic induction, the Faraday effect, benzene, and the laws of electrolysis. His 1834 paper on electrical decomposition established the quantitative foundation of electrochemistry. Faraday refused knighthood and titles, remaining humble throughout his life. He introduced the terms electrode, anode, cathode, and ion. Quiz time. According to Faraday's first law, what happens when you double the current passed through an electrolytic cell? Option A, the voltage doubles. Option B, the mass deposited halves. Option C, the mass deposited doubles, assuming same time. Option D, the temperature of the solution doubles. The correct answer is C. If the current doubles and time stays the same, the charge doubles, so the mass deposited doubles. Quiz 2. The Faraday constant F equals 96,485 coulombs per mole. What does it represent? Option A, the charge of 1 electron. Option B, the charge of 1 mole of electrons. Option C, the energy of 1 mole of photons. Option D, the mass of 1 mole of protons. The correct answer is B. F is the charge carried by 1 mole of electrons. It is Avogadro's number times the elementary charge. Quiz 3. For two different ions with the same charge passed, which one deposits a greater mass? Option A, the ion with higher molar mass. Option B, the ion with higher valence. Option C, the ion with lower molar mass. Option D, they both deposit the same mass. The correct answer is A. From the equation m equals ITm over Fv, with the same charge, mass is proportional to m over v. Higher molar mass with the same valence means greater mass deposited. Quiz 4. During water electrolysis, what is the volume ratio of hydrogen gas to oxygen gas produced? Option A, 1 to 1. Option B, 1 to 2. Option C, 2 to 1. Option D, 3 to 1. The correct answer is C. The overall reaction 2H2O produces 2H2 and 1O2. So the hydrogen to oxygen volume ratio is 2 to 1. Quiz 5. Which metal ion requires the most charge to deposit 1 mole of metal? Option A, silver plus with valence 1. Option B, copper 2 plus with valence 2. Option C, aluminum 3 plus with valence 3. Option D, sodium plus with valence 1. The correct answer is C. Aluminum 3 plus requires 3 electrons per ion, that is 3 Faradays of charge per mole. more than copper's 2 Faradays and silver's 1 Faraday. Problem 1. A current of 3 amperes is passed through a copper sulfate solution for 45 minutes. What mass of copper metal is deposited on the cathode? First, write the half reaction. Copper 2 plus 2 electrons gives copper solid, so the valence V equals 2. Convert time to seconds. 45 minutes times 60 equals 2,700 seconds. Calculate the charge. Q equals I times T, which is 3.00 times 2,700 equals 8,100 coulombs. Now substitute into Faraday's equation. M equals Q times M divided by F times V. That is 8,100 times 63.55 over 96,485 times 2. This gives 2.67 grams of copper. Problem 2. A jewelry manufacturer wants to deposit 10 grams of silver onto a decorative item in 2 hours. What current must be applied? The half reaction is silver plus 1 electron gives silver solid, so V equals 1. Convert time. 2 hours times 3,600 equals 7,200 seconds. Rearranging Faraday's law to solve for current. I equals M times F times V divided by T times M. Substitute 10.0 times 96,485 times 1 divided by 7,200 times 107.87. This equals 964,850 over 776,664, which gives 1.24 amperes. Problem 3. An aluminum smelter operates a Hall-Héroult cell at 150 kiloamperes for 12 hours. What mass of aluminum is produced? The half reaction is aluminum 3 plus 3 electrons gives aluminum solid, so V equals 3. Convert time. 12 hours times 3600 equals 43,200 seconds. Current is 150,000 amperes. Calculate charge. Q equals 150,000 times 43,200 equals 6.48 times 10 to the 9 coulombs. Now substitute. M equals 6.48 times 10 to the 9 times 26.98 divided by 96,485 times 3. This equals 604 kilograms of aluminum. Problem 4. Water electrolysis produces hydrogen and oxygen gas. A current of 10 amperes is passed through acidified water for 30 minutes. At STP, what volume of each gas is produced? First, the cathode reaction. 2H2O plus 2 electrons gives H2 plus 2OH minus, with V equals 2 per H2 molecule. The anode reaction. 2H2O gives O2 plus 4H plus 4 electrons, with V equals 4 per O2 molecule. Total charge. Q equals 10.0 times 1800 equals 18,000 coulombs. Moles of H2 equals 18,000 divided by 96,485 times 2 equals 0.0933 moles. Volume of H2 equals 0.0933 times 22.4 equals 2.09 liters. Moles of O2 equals 18,000 divided by 96,485 times 4 equals 0.0466 moles. Volume of O2 equals 0.0466 times 22.4 equals 1.04 liters. Problem 5. A chrome plating factory operates a bath at 500 amperes. How many minutes are needed to deposit 250 grams of chromium from chromium 3 sulfate? The half reaction is chromium 3 plus 3 electrons gives chromium solid, so V equals 3. Rearranging Faraday's law for time. T equals M times F times V divided by I times M. Substitute values. 250 times 96,485 times 3 divided by 500 times 52.00. This gives 72363,750 divided by 26,000 equals 2,783 seconds. Convert to minutes. 2,783 divided by 60 equals 46.4 minutes. Let us bring everything together. Faraday's first law tells us the mass deposited is proportional to the charge passed. The second law tells us that for the same charge, different substances deposit in proportion to their equivalent weight. The combined equation M equals ITM over FV is the workhorse of electrochemistry. The Faraday constant F equals 96,485 coulombs per mole and connects the macroscopic world to the atomic level. From electroplating jewelry to refining copper to splitting water for green hydrogen, Faraday's laws remain as relevant today as they were in 1834.